Two cosmic forces nearly cancel each other, expansion and gravity. Here is the twist, and it changes everything. That balance is real, but never static, ever. The immediate takeaway is simple and surprisingly practical. The universe looks calm because flows regulate extremes. Galaxies form, then feedback cools the frenzy quickly. Structures grow, yet expansion keeps them from collapsing everywhere. Small ripples seed order instead of runaway chaos. We can watch this balance on every scale, from sound waves in plasma to today's quiet nights. Stare at a spiral galaxy, arms stretched like a frozen whirlpool. Nothing holds still, yet the shape endures for billions of years. That steady look hides a dynamic balance at work. Dynamic balance means pushes and pulls cancel, on average, over time. It matters because enduring shapes let complexity build and survive. Gravity clumps matter toward centers, carving spirals and bars. Cosmic expansion stretches distances, thinning out large-scale density. The two tug constantly, but neither wins everywhere. Rule of thumb, structures hold when gravity beats local expansion. Dark matter adds invisible mass, deepening the gravitational wells. Gas falls inward, heats up, and radiates that heat away. Radiation is the brake that prevents runaway collapse for now. Meanwhile, space expands faster between faraway clusters and voids. So local islands grow, while the ocean slowly widens. Example in real terms with one helpful number, at 1 megaparsec, Hubble expansion is about 70 kilometers per second. A galaxy pair that close can still bind and orbit. The local group spans a few megaparsecs and stays together. Beyond clusters, expansion wins and distances grow relentlessly. Net result, islands of order persist inside a widening universe. Wind back the clock to a foggy, glowing baby universe. It looked uniform, yet tiny ripples hid inside the light. Inflation is a burst of ultra-fast expansion right after. It matters because it smooths space and flattens curvature. Flatter space means gravity and expansion start nearly balanced. During inflation, distances grew almost exponentially in a heartbeat. Curved regions stretched thin, like wrinkles pulled across rubber. Quantum jitters froze into seeds, tiny but everywhere. Those seeds had amplitudes around 1 part in 100,000. That small number keeps early chaos gentle and predictable. After inflation ended, gravity amplified the seeds slowly. Hot plasma pushed back, making waves instead of breakups. Those waves still imprint the sky as delicate modeling. Look at the microwave background and you see that speckle. Average temperature barely varies by only 1/10,000th. That uniformity sets the stage for balanced growth later. So the picture is this: smooth beginnings keep growth orderly. Now imagine a full sky map, sprinkled with blue and red freckles. Those freckles are sound waves, frozen when atoms first formed. Acoustic balance here means pressure and gravity trade momentum cleanly. It matters because these waves are rulers written across space. Hot plasma pushed out, gravity pulled in, and oscillations grew. When light decoupled, the waves stopped and left rings. Those rings set a standard size, the sound horizon. It spans about 150 megaparsecs in today's scale. On the sky, that projects to roughly 1 degree. Satellites measure peaks at that scale and multiples. The pattern reveals cosmic ingredients like a recipe list. Numbers pop out cleanly with small statistical error bars. About 5% is atoms, mostly hydrogen and helium. Roughly 27% is dark matter, unseen yet gravitational. The rest is dark energy, around 68%. Those proportions let galaxies grow without collapsing too fast. Quick test: does the first peak sit where flat space predicts? Yes, within tight error, space looks very nearly flat. Bottom line, waves kept early growth rhythmic, not chaotic. Drift into a dark nebula where newborn stars carve glowing cavities. Clouds look chaotic, yet star birth rates barely budge. Self-organized criticality describes systems hovering near a tipping point. It matters because near-critical systems regulate themselves without controllers. Gravity tries to collapse clumps while turbulence stirs them apart. Magnetic fields thread gas, adding tension and friction. Young stars blast ultraviolet light, heating and blowing bubbles. Supernovae detonate later, injecting momentum and heavy elements. The net effect is a thermostat around a fragile threshold. Example: in real terms, the efficiency stays tiny. Only about 1 to 2% become stars each cycle. That slow pace persists across clouds over millions of years. A single supernova releases about 10 to the power of 44 joules. That blast sweeps gas, quenching collapse in the neighborhood. Radiative cooling then settles clouds, readying the next round. The cycle keeps rates steady despite messy local turbulence. Observations match across galaxies with wildly different masses. In dwarfs and giants, efficiencies stick near a few percent. Bottom line, birth and blowback hold star factories near balance. Fly toward a galaxy cluster core, packed with shimmering galaxies. Stars streak by, yet average motions look surprisingly stable. Virial equilibrium is when random motions balance gravitational pull. It matters because it sets sizes, temperatures, and velocities. Kinetic energy counters potential energy, roughly in fixed proportions. Encounters and mixing spread energy until the ratio settles. Gas shocks convert infall speed to heat, then radiation. Dark matter guides the dance, shaping the overall potential. Example with numbers helps ground the picture. The Milky Way halo weighs around 1 trillion solar masses. Typical star speeds are 150 to 200 kilometers per second. The virial radius spans about 200 kiloparsecs, give or take. In clusters, galaxy speeds reach 1,000 kilometers per second. Yet the overall profile stays steady for billions of years. So gravitational wells look calm because random motion carries load. Net result, halos convert chaos into temperature and pressure, then glow. Step back to a map of the cosmic web like lace. Filaments stretch for hundreds of millions of light years. Balance here means steady flows feed nodes without choking them. It matters because networks self-regulate through routing and queues. Gravity drags matter along filaments into cluster basins. Shocks heat gas at boundaries, slowing the plunge. Some gas cools and sinks, forming stars in galaxies. Outflows from feedback blow material back, enriching surrounding streams. Example in scale, a filament can span 300 megaparsecs. Cluster nodes often weigh around 1 quadrillion solar masses. Gas flows inward at hundreds of kilometers per second, yet the scaffold endures for eons with slow remodeling. Bottom line, traffic rules beat pileups across the cosmic network. Drop into a galaxy center where jets lance from a core. That core is a supermassive black hole, quietly accreting gas. AGN feedback means the core returns energy to its host. It matters because it prevents a cooling catastrophe in giants. Magnetic fields collimate jets, which punch bubbles into hot halos. Shocks heat ambient gas, stopping rapid condensation and starbursts. Turbulence spreads energy broadly, like stirring a thick soup. The engine cycles on and off, tracking the fueling rate. Example number, an outburst can carry between 10 to the power of 52 joules. Some reach about 10 to the power of 54 joules. That rivals the binding energy of dense central gas. In clusters, cavities expand for tens of millions of years. Cooling times stretch to 1 billion years or more. Net result, black holes act like thermostats for galaxies. Stand on a quiet planet, warm under a gentle star. The scene feels normal, but that normal is selected. Anthropic selection means observers appear where conditions allow observers. It matters because perception favors balanced pockets over extremes. Galaxies with brutal bursts may lack long, stable windows. Quiet spirals can host chemistry for billions of years. Mechanically, selection multiplies probabilities across time and space. Regions with steady feedback produce more chances to notice them. Example close to home, sunlight at Earth varies by only a few percent yearly. Climate stability stretches thousands of years between violent flips. Our position within the galaxy avoids frequent sterilizing blasts, so our memories prefer balance because chaos silences witnesses. We should be careful not to mistake selection for design. Bottom line, you see balance partly because you could. The universe looks balanced not because it is quiet. It is loud, but its loudness runs on feedback loops. Expansion stretches, gravity gathers, and the middle holds. Inflation smoothed the start, planting gentle, countable seeds. Sound waves kept rhythm, encoding a cosmic ruler. Dark matter halos traded motion for heat and light. Star birth regulated itself through winds and explosions. Black holes heated halos, throttling runaway cooling in giants. Web filaments routed traffic, feeding nodes without gridlock. Selection shaped our view, favoring islands that allow witnesses. So balance is real, but always dynamic and earned. If that clicked, share this with a curious friend. Thanks for listening and sleep under a calmer sky tonight. Net result, the cosmos holds together by constant negotiation.